Welcome everyone, I'm Jim Corkins, and we are now in the fourth part of our voltage and electric potential energy module. So again, if you haven't done the reading, please do so. So starting off, this is the derivation, or how we got to calculate the potential energy of point charges due to another charge causing a force on it. So potential energy, if you remember from your 111 and 121 courses, is the integral of force versus distance, right? Or if you're 111, it's just force times distance, right? Well, force, electric force, in this case, is KQ1 Q2 over R squared. And that was in the, I believe it was in 1.2 of this class, okay? And so when you integrate that, you end up getting KQ1 Q2 over R. And if we move Q1 to the front, then we get Q1 KQ2 over R. In other words, the potential energy is equal to, is a voltage acting on a charge, okay? Again, a voltage is a height, and so this charge would be changing its voltage. It'd be moving from one voltage to a different voltage. It would be changing its position right there. And so with electric fields, though, the derivation is a little bit easier. Electric force is just Q1 times the electric field and across a distance. So for 111, it would be Q1 negative E2 dr. And then when you multiply that out, that negative E2 becomes a positive V2, and you get the same thing. And so if you want to calculate a voltage, and you've got a potential energy and a charge that is in that potential energy field, and this is electric potential energy, you could use that to calculate the voltage, okay? But again, voltage is a height. So moving over here, we have to think about potential voltage as a height. So here is our voltage map, much like a gravitational potential energy, right? So if you're trying to push a ball uphill, okay, so you're increasing its height, okay, so we got that mass right there. The height is going up, the mass is unchanging, and so since the height is increasing and you're moving it uphill, the potential energy is going to be increasing as you move it uphill. If the height is decreasing, the potential energy is also decreasing, okay? Well, if you have a positive charge right here, this is our little Q1, and we're trying to move it closer to this Q2 right here. So this is our Q2 here, which is causing a voltage at these different points. Okay, it would feel like, just like in this case, that you're moving this positive charge uphill, right? So from this little Q1's perspective, it sees a mountain that it has to climb up. Okay, so both of these are essentially the same concept. The potential energy due to gravity would be increasing here. And since you're multiplying a positive Q times a positive voltage, right, those are positive heights, that since the voltage is increasing here, the potential energy would also be increasing here. This is similar to potential energy due to springs, okay? So in 111, when you push a spring and start to compress it, your hand is pushing it to the right. The spring would be pushing it, be working against you. So you would be doing work and the spring would be working against you. So you'd be increasing the potential energy of that spring. Okay, whenever a spring is compressed or stretched past the equilibrium, it takes work to do that. And so that potential energy to that spring is 1/2 kx squared. Well, that potential energy to a spring is just like you taking a positive particle and pushing it closer to a group of positive particles. You'd be doing work, your hand would be doing work, pushing it to the right, and the electric field caused by these guys and their voltages would be trying to push you to the left. Okay, trying to push you downhill. Similarly, with electric fields, if you have a positive charge, and that means you have positive plates over here since the electric field is pointing to the left, you would be pushing this positive charge uphill with your hand, and the electric field would be trying to push it downhill. Okay, so all of these things are really the same concepts. Okay, so potential, we are going to be begin working with energy again here in the actual next part of this module. But we have to introduce the concept of potential energy, not due to gravity, potential energy due to a charge, which is Q times V. So in other words, U sub Q, we have our little Q1, it's going to be Q1, and since we're dealing with a charges in this case, it'd be K Q2, or all of those Q2s over R, or it would be U sub Q and Q1 times a negative E dot R. Okay? It would be one of these two things. Basically, whichever interpretation of voltage, if you have a charges working on that, you would just substitute in the voltage due to a point charge. If you're working in an electric field, you have to use this interpretation. Okay, but basically, you have increased the electric potential energy is similar to gravitational potential energy and springs. Okay. So let's go ahead and try this out. Let's try working on a concept problem. So here you're going to be moving a group of charges together. So from really far out, an infinite distance away where R is infinity, into where they're a distance d away from each other. And the question is which one is going to make you do more work? A, B, or will they be the same? With A, you're moving a positive 1 charge within a distance, from an infinite distance to a distance d away from this positive 2 charge. In this other case here, you're taking all three of these charges that are an infinite distance away from each other and pushing them closer to the distance d away from each other. So which one is going to take more work, or are they the same? All right, pause the video now. Now, in my class, in Physics 111, I taught you how to approach all energy problems. You compare the initial energy to the final energy. And so that initial energy, we had a list, but it was Ki plus U sub Gi, and then we had plus U sub spring, this is the spring energy, and then we had work. And that is going to be equal to the final energy, which is the counterparts to this. Okay? It's U sub GF, the gravitational, plus U sub spring F, plus, actually there is nothing else there. Okay, so in Physics 111, we just had 1, 2, three different energies to work with. And work would be work due to friction or work due to a force, where work is equal to a force times a displacement, right? Anyways, now we're adding U sub q I plus U sub q F. So once we have our energies listed out, here's how we're going to approach this. And these energies are actually question marks. They're at an infinite distance away initially, not moving. So are they not moving? Do they have a kinetic energy, or are they moving? No. Are you close to the Earth? No. Is a spring touching it? No. All right. You are doing work. In the end, when you bring them close to each other, you're holding them in place. So they're not moving there. You're still not near the Earth, and there's no springs touching you. Okay? And we don't actually have to calculate the force. So U sub qi plus work equals U sub qf. And just to point out, we're dealing with point sources, so that this is going to be Q. U sub qi is actually, this positive Q is going to be this guy, positive 1Q here. So let's just do this one first. And the voltage is the initial voltage at that distance. So this is what gives it the I to it. In this part, we're doing U sub q. We're still moving that q, but now it's going to be distance within a distance 1d away. Now, we're going to add some nuances to this. K, Q, this would be due to a positive 2Q, so the voltage of this charge is causing a voltage on this guy, and it's a distance, well, it's in the beginning, and it's an infinite distance away. So this would just be infinity on this. Plus work equals positive 1Q, K times positive 2Q, all over a distance d apart. Now, 1 over infinity, this approaches, this is 0. So this is going to be positive 1Q times 0 plus work. So this is just, this whole thing is just 0. This is going to then be, now I'm going to multiply all that together, positive 2KQ squared over D. Okay, so that is the work to put that, oh, I don't know why it's doing this. That is the work to put A together, all right? Now I'm going to move that to the side, and I'm going to do this part again. Actually, I'm going to do all the way to this part. Oh boy. Anyways, let's go ahead, and I'm going to just start from scratch. No. Let me go ahead and try this. I can do it, I think. Boy. Okay, hold on a second. I'm going to fix this. Okay, so this part is for the 3 particles. Okay? So, just like we learned, they're all at an infinite distance away, and technically there would be 3 different initial potential energies, right? Three particles, 3 different potential energies, and there would be 3 different final potential energies as well. Okay? But how we just learned, if they're an infinite distance away, because I want to get to the point, those initial energies are 0. Now, when we put these together, okay, so I'm basically getting to this point right here, we're going to take this positive Q. This positive 1Q is being acted upon by this other positive 1Q, so that's going to be K times positive 1Q, and they're a distance d apart. Okay, now let's do this guy being acted upon by this guy. So that is going to, let's do this guy being acted upon by this guy. So these two we already took care of, and that's their mutual potential energies. Let's do this interaction there, which is going to be positive 1Q, K times positive 1Q, all over distance d apart. And then let's do this interaction, the energy it takes to put those two guys together. So positive 1Q, K times positive 1Q, all over distance d. So the work here is going to be KQ squared over d plus KQ squared over d plus KQ squared over d. So working this out, the amount of work to take to put all three particles together would be positive 3KQ squared over d. So B would take more work to do. Okay. When we get into potential energy, when we get into energy part of this in the next part, I'll get more into this procedure to follow. So B. All right. Let's do the other two conceptual questions. Okay. So below we have a set of electric fields due to capacitors, and we have electrons moving within those electric fields. This electron is moving downwards in the direction of the electric field. This electron is moving to the right while the electric field is pointing down, and this electron is moving upwards. So your job is to decide whether the electric potential energy is increasing, decreasing, or is 0. So try this out, pause the video. Okay, so this is a negative plate. These are the negatives and the positives are just above it. So we know that. So we know this is moving at this instant. The voltage, I'm just going to lay this out as 0 voltage, negative 1 volt, got to put a number in it, and this would be positive 1 volt. So the electric potential energy acting on this negative 1Q is going to be, here's the basic equation right here, which is voltage, and then we got the negative Q, and then Q, and remember voltage is negative E dot R. So this is going to govern all of these problems right here. Right here. I'm going to put this right off to the side. So if we're going to calculate this, we're just going to use the negative voltage, right? So this U sub Q, we're just going to hack it. That's a negative charge, and it's going from 0 volts, and we should put a delta V there. It's going from 0 volts to negative 1 volts. So it's going to end at negative 1 volts minus 0 volts. So when we calculate that, we're going to get negative Q times a negative 1V. So that's going to be a negative, no, that'll be a positive Q times V. So this is going to end up being increasing. you're increasing the potential energy. Positive would be increasing the potential energy. Negative would be decreasing the potential energy. All right, here, well, this negative charge is just moving along the 0 volts. So U sub Q, we're going to have a negative Q, but its final position and its initial position are both 0. So it's moving along the potential line, which means that U sub Q is equal to 0. So this is 0. This one is starting out at 0 volts and it's ending up at a positive 1V. Here would be the negative 1V. Negative 1V. So this U sub Q is going to be a positive 1Q. And, oh, sorry, that should be a negative 1Q. Forgot to put the 1 right here. And its final voltage is a positive 1 volt. Its initial voltage is 0 volts. U sub Q. So this guy's potential energy is going to be negative QV. So this is going to be a negative potential energy, which means our potential energy is decreasing as it's moving. Okay? It may be moving in the positive voltage direction, but for this guy, when it's moving opposite the direction of the electric field, and the electric field vectors are pointing here, it's actually moving downhill from its perspective. It's kind of interesting. So electrons always want to move upstream, but from its perspective, it's actually moving downhill. So, kind of cool. This is the positive versions of this, and in this case the electric field is pointing to the left. Okay, so why don't you go ahead and try this one. Pause the video now. Okay, well, here would be the negative voltage. So negative voltage, this is going to be 0. And this will be positive voltage, right? And I'll just mark these other ones up. Negative voltage, 0, and positive voltage. Here is negative voltage. This is 0 voltage. And this is positive voltage, right? So in this case, this guy is just moving on that potential line. So this potential energy is a positive Q, where its potential voltage change is 0. So this is equal to 0. Here, the electric field is pointing to the left. This guy, this positive, is moving upstream. So we're going to have a positive Q, and its ending voltage is positive V. Its starting voltage is 0. So U sub Q, that should be a Q, is going to be positive Q times voltage. So its potential energy is increasing. Finally, the positive here is moving downstream. And if it's moving downstream, its voltage is decreasing, and so its potential energy is decreasing, right? Positive Q, negative V plus 0 is the starting voltage. So this is just going to, again, be negative Q times V. So this is decreasing. Okay. So hopefully this is a good introduction to you for what electric potential energy is. We do have a tutorial, which I will do an introduction to that shortly. But I want you to practice all of these, okay, tutorials. And there is a conceptual quiz related to this. So between the conceptual quiz and the tutorial, your conceptual understanding of electric potential energy will be really great. That way, when we start integrating electric potential energy with your other energies that you learned in Physics 111, you'll already have a really good foundational understanding. All right, have a great day.